Hi, in this video I'm going to explain how to use prime factorization to find the least common multiple of two numbers. First, let's talk about what that word multiples means. You may already be familiar with factors. Factors are the numbers which can divide a specific number. So for example, 3 and 5 are factors of 15. Multiples, on the other hand, are what you get when you take a number and multiply it by an integer. So the multiples of 30 are 30 times 1, 30 times 2, 30 times 3, etc. So if we list those out for 30, it looks like 30, 60, 90, 120, 150, and so on. And the multiples of 50 would be 50, 100, 150, 200, etc. Now we're looking for any multiples which are common to both 30 and 50. So what shows up in both lists? We can take a quick look and see that both lists contain 150 and 300. And if we were to continue listing more multiples of 30 and 50, we'd see more common multiples come up. Now we're ready to find the least common multiple, which is our real goal. So we can look at the common multiples that we've found and identify which one is the least, the smallest, or the first one that shows up. That's 150. Before that, there are no common multiples, and all the ones after that are greater. 300, for example, is a common multiple, but it's not the least common multiple. So now that you've seen what the least common multiple means, is that the easiest way to find it, just listing out the multiples of two numbers until you hit on a common multiple? Really, it's much easier to use prime factorization to quickly identify the least common multiple. So let's look at that same example of 30 and 50 and find the least common multiple using prime factorization instead. Now we can compare the prime factorizations 2 times 3 times 5 and 2 times 5 times 5. Remember before when we talked about greatest common factor, we were looking for only what both prime factorizations contained. The least common multiple is different. Here we're trying to build a number that has everything that both numbers need without anything extra. So for example, the prime factorization of 30 is 2 times 3 times 5. That means the least common multiple has to contain at least a 2, a 3, and a 5. And then for 50, we have 2 times 5 times 5, meaning the LCM needs to contain at least a 2, a 5, and a 5. But if we start with 2, 3, 5, and then go and check on what 50 needs, we can see we've already got a 2 and already got a 5. We just need one more 5 to satisfy the prime factorization of 50. So the LCM, which is the smallest collection of prime factors that satisfies both prime factorizations, is 2 times 3 times 5 squared, which is 150. And you can see this was a more direct way of finding it than listing out all the multiples. Now you might be thinking, this is unnecessary. It was so easy to list the multiples of 30 and 50, and it was so obvious that 150 was their least common multiple. Why bother using prime factorization? That's all well and good for numbers like 30 and 50, but what about this next pair, 56 and 980? I don't know about you, but I don't know my 56 or 980 timetables offhand, and the numbers are going to get big really fast. Using prime factorization will actually be a lot easier. Now we can compare these two prime factorizations, 2 times 2 times 5 times 7 times 7, and 2 times 2 times 2 times 7. Remember, the LCM is not about finding what these two prime factorizations share. It's about building a number that contains everything that meets the needs of both without any extra. So we can see we're going to need some 2's, and one of these prime factorizations needs 2 2's and the other needs 3. So our LCM needs 3 to satisfy both of them. We don't need 5 2's to satisfy them simultaneously, we just need enough for either one. You can see that one prime factorization has a 5 and the other doesn't, so we just need one 5. And then we've got 7 times 7 in the top and 7 in the bottom, so 7 times 7 will be enough to satisfy both. And when you multiply all that together, 2 cubed times 5 times 7 squared, that's 1960, the LCM of 56 and 980. Now suppose we compared these prime factorizations written with exponents instead of repeated multiplication. So 2 cubed times 7 and 2 squared times 5 times 7 squared. Again, we want the LCM to have enough for each of these prime factorizations to be satisfied, so we clearly are going to need some 2's, some 5's, and some 7's. When it comes to figuring out how many of each, we can look at the greater exponent in each prime factorization. So if we have 2 cubed and 2 squared, we know that the LCM will have to have 2 cubed in order to satisfy the prime factorization that has the greater need. Then we've got a 5 in one and no 5 in the other, so again we just need the 1 5. And lastly we have 7 squared and 7, so 7 squared in the LCM will satisfy both. Let's look at one more example, finding the LCM of 675 and 495 by first finding the prime factorizations. That's a wrap for now on prime numbers, prime factorizations, greatest common factor, and least common multiple. If you have any specific topics in mind that you're curious about, please let me know. Thanks for watching, and I hope you enjoyed.